So here begins the official start of integral calculus. And so this is a very important section. We are looking at the fundamental theorem of calculus. So let's jump right in. For the fundamental theorem of calculus, we want to let f be a continuous non-negative function on a closed interval such that x is greater than or equal to a, less than or equal to b. So let's start just by thinking about this area graphically. And we are familiar with what the sketch should look like here. So here's our coordinate plane. We've got the y-axis and the x-axis. And somewhere here is a beautiful continuous and non-negative curve. Y is equal to f of x. And we're only really concerned with here what's going on between the endpoints A and B, and above that x-axis. So the area that we're thinking about is under this curve and above the x-axis. Now for the fundamental theorem, we're only going to think about a portion of this. So if y equals the antiderivative capital F of x on a closed interval from a to x of f of t dt, represents the area under the curve on an interval, a closed interval, from a to x. So looking back at our picture here, we're just thinking about some arbitrary x value, and we want to think about this area here from a to x. And don't be frightened by that t. We've already used x as the upper bound here, so we need another variable, right? Because remember, a definite integral depends on the function, not the variable. So, using this, keeping in mind that we are letting y be the antiderivative of the definite integral from a to x of f of t dt, what the fundamental theorem tells us is that if we differentiate this with respect to x, so if we take the d dx of both sides here, what we end up with is the original function. So the derivative of y, if we differentiate the antiderivative, we end up with f of x. So we take this upper bound and plug it right into the function. And you can even note here that this is technically multiplied by the derivative of x, which is just 1. So this gives us f of x. So differentiating a definite integral with respect to x gives us the original function. So this can be a little bit tough to swallow the first time that you see it. So what I'd like to do is look at this and verify this property, or verify this theorem. Verify the conclusions of the fundamental theorem of calculus by first evaluating the definite integral and then differentiating the result. So before we do this, let's actually think, just so we can really prove to ourselves that this fundamental theorem does work, let's apply the fundamental theorem here. So the fundamental theorem of calculus. So by the fundamental theorem of calculus, if we have y is equal to the definite integral from 7x squared sine of 2t dt, the fundamental theorem tells us that this should be, if we differentiate both sides with respect to x, that dy dx is going to be equal to, we take our upper bound, plug it in for t, and then multiply by the derivative. So dy dx should be equal to sine of 2x squared multiplied by the derivative of x squared. So dy dx should be equal to sine of 2x squared multiplied by 2x. So, well, we want to verify this. We want to make sure that this is actually holding true, and we can easily verify the fundamental theorem of calculus by first evaluating the definite integral and then differentiating the result. And the result should give us sine of 2x squared times 2x. So let's take a look. Step 1, we got to evaluate this definite integral. So we have, again, y is equal to the definite integral from 7 to x squared of sine of 2t dt. So this integrates to minus cosine of 2t divided by 2, which we can now evaluate from 7 to x squared. So we need a little more room. So let's do this. We're going to have, I'll keep that negative 1/2 on the outside. So this is minus 1/2 multiplied by cosine of 2x squared minus cosine of 2 times 7, which is 14. So there we go. We have y is equal to negative 1/2 multiplied by cosine of 2x squared minus cosine of 14. So now we need to differentiate this result to confirm that fundamental theorem. So we are going to differentiate both sides of this equation with respect to x. So we have y is equal to negative 1/2 multiplied by cosine of 2x squared minus cosine of 14. And we want to now go ahead and we're going to differentiate, again, both sides here with respect to x. So taking the ddx of both sides, this leaves us with, we have the derivative of y with respect to x, or dy dx, is equal to, we'll keep that negative 1/2 on the outside here. And differentiating cosine of 2x squared, this leaves us with minus sine of 2x squared multiplied by the derivative of 2x squared, which is 4x. And then this is minus, we have the derivative of cosine of 14, which is just a constant, so that goes to 0. And we can simplify. So we have a negative multiplied by a negative to give us a positive. And we know that the 2 in the denominator will go into 4 in the numerator 2 times. And this leaves us with dy dx, which is equal to positive sine of 2x squared multiplied by 2x, which is what the fundamental theorem of calculus told us. So there we have it. We have verified our fundamental theorem of calculus. So you can see how much faster it is to apply our fundamental theorem of calculus. And it's confirming to us that differentiating a definite integral with respect to x gives us that original function,